What if I told you that right now, sitting somewhere in a spreadsheet on my computer, there is a planet that does not exist anywhere in the universe, a planet that you helped build, a planet with a mass you chose, a star you picked, an atmosphere you argued about in the comment section for 3 days straight. And when I ran that planet through the same kind of physics simulations that real astrophysicists use to test exoplanet habitability, something happened that I genuinely did not expect. And by the end of this video, you are going to know exactly why. Because today we are not just talking about alien worlds we might one day discover. We are building one from scratch using thousands of votes from this very audience. And then we are going to find out together whether the world you design could actually support life, or whether it would be a dead, frozen, boiling, radiation-blasted rock spinning uselessly around a star that never asked to host it. Before we get into the results, I want you to understand why this experiment matters, because this is not just a fun thought exercise. It is actually a legitimate scientific method. Astrobiologists and planetary scientists build exactly these kinds of synthetic planets all the time. They take a set of variables, star type, orbital distance, planetary mass, atmospheric composition, rotation speed, magnetic field strength, and they run them through climate models and habitability equations to predict what conditions would be like on a world we have never seen and may never visit. This is exactly how scientists study exoplanets that are hundreds of light years away, worlds we can only detect through tiny dips in starlight or minuscule wobbles in stellar motion. We cannot send a probe to Kepler 186f or TRAPPIST-1e in our lifetimes, so instead we build them in code. We simulate their atmospheres, their temperatures, their potential for liquid water, and we make our best scientific guess about whether life could exist there. That is precisely what we are doing today, except instead of scientists in a lab picking the numbers, it was you, thousands of members of this community, voting, debating, and building a world together. So let me walk you through how this all started. A few weeks ago, I opened up a public poll and a series of community discussions asking you to make the fundamental choices that define a planet. I broke it down into categories that mirror exactly what real planetary scientists consider when they assess habitability: the type of host star, the orbital distance from that star, the mass and radius of the planet itself, the composition of the atmosphere, the presence and strength of a magnetic field, the rotation period, meaning how long a day lasts, the axial tilt, which determines the severity of seasons, the number and size of moons, and finally, the percentage of the surface covered in liquid water. Each of these choices has enormous consequences, and the beautiful thing about this experiment is that you did not just pick things that sounded cool. You actually debated the science behind them, and I watched genuine, informed astronomy discussions unfold in real time, which honestly gives me a huge amount of hope for how curious and capable this community is. Let us start with the star, because everything about a planet's fate begins with the star it orbits. The community was given 4 real categories of stars to choose from, each based on actual stellar classifications. The first option was a hot blue-white star, similar to Sirius, a star that burns incredibly bright and hot but has a short lifespan measured in a few 100 million years, far too short for complex life to ever evolve, because on Earth it took billions of years just to get from single-celled organisms to anything resembling intelligence. The second option was a yellow sun-like star, similar to our own, a G-type main sequence star with a lifespan of around 10 billion years, stable, long-lived, and exactly the kind of star that gave Earth enough time to cook up everything from bacteria to blue whales. The third option was an orange dwarf, a K-type star, slightly cooler and dimmer than the Sun, but with an even longer lifespan, sometimes exceeding 20 or 30 billion years, which many astrobiologists now consider to be an even better candidate for hosting stable, long-term habitability than our own Sun. And the fourth option was a red dwarf, an M-type star, the most common star in the entire galaxy, incredibly long-lived, Some red dwarfs will still be burning steadily long after our own sun has died. But red dwarfs come with serious complications, intense flare activity, and planets close enough to be in the habitable zone often become tidally locked, meaning one side always faces the star in permanent day while the other side is locked in permanent night. The community vote was close, but in the end, the orange dwarf star won by a significant margin, and honestly, I think that was a smart choice, because it strikes a rare balance between stability and longevity without the extreme flare hazards of a red dwarf. We named this star Hellion Minor for the purposes of our simulation, a K-type orange dwarf star, about 70% the mass of our Sun, with a surface temperature a bit cooler than our Sun, but still bright enough to support strong photosynthesis on a properly positioned world. Next came orbital distance, and this is where things got genuinely tense in the community discussion, because everyone understood the core concept of the habitable zone, sometimes called the Goldilocks zone, the region around a star where temperatures allow liquid water to exist on a planet's surface, not so close that oceans boil away, not so far that they freeze solid. But the habitable zone is not a simple fixed ring. It shifts depending on atmospheric composition, planetary albedo, meaning how much light the surface reflects, and even cloud cover. The community was given a range of orbital distances to choose from, expressed as a fraction of the habitable zone width. And after significant debate, the audience settled on a position toward the inner edge of the habitable zone around Hellion Minor, reasoning that a slightly warmer world would offset the star's cooler output. This is actually a real strategy used in exoplanet habitability modeling, because a star like Hellion Minor emits less overall energy than our Sun, so a planet sitting closer in can still receive an Earth-like amount of solar energy without frying. Then came the planet itself, its mass and radius, and here the community leaned heavily into the science of what is called a super-Earth, a rocky planet larger than our own but smaller than gas giants like Neptune. The audience voted for a planet with approximately 1.4 times the mass of Earth and a radius roughly 1.1 times Earth's radius. This decision has massive downstream consequences. Because a more massive rocky planet holds onto its atmosphere more effectively through stronger gravity, it is likely to retain more internal heat for a longer geological lifespan, which matters enormously for maintaining a strong magnetic field, and it can support a thicker atmosphere that provides better greenhouse insulation and radiation shielding. Higher gravity also means geological activity like volcanism and plate tectonics can persist longer, and plate tectonics, as strange as this sounds, is actually believed to be one of the most important stabilizing mechanisms for a planet's long-term climate, because it recycles carbon dioxide between the atmosphere and the interior of the planet, acting like a planetary thermostat over geological timescales. Now we come to the atmosphere, and this is where I saw some of the most sophisticated community debate of the entire project. You were given sliders, essentially, to construct an atmospheric composition, choosing percentages of nitrogen, oxygen, carbon dioxide, water vapor, and trace gases. The final community composition ended up remarkably close to Earth's own atmosphere, 76% nitrogen, 20% oxygen, a bit over 1% carbon dioxide, which is actually significantly higher than Earth's current carbon dioxide levels, and the remaining fraction split between water vapor and trace gases like argon and methane. That elevated carbon dioxide level was actually a smart compensatory choice, because remember, this planet orbits a slightly cooler star, so a bit of extra greenhouse gas helps trap enough heat to keep the surface temperature in a livable range, offsetting the star's lower energy output. Atmospheric pressure was the next major decision, and the community chose a surface pressure about 1.3 times that of Earth, which makes sense given the increased planetary mass and the resulting stronger gravitational pull retaining a denser gas envelope. A thicker atmosphere like this would also provide better protection against incoming micrometeorites and would do a superior job of distributing heat around the planet through stronger atmospheric circulation, potentially reducing the temperature difference between the equator and the poles compared to Earth. The magnetic field came next, and I want to spend real time on this because it is one of the most underappreciated factors in planetary habitability. A planet's magnetic field is generated by convection currents in a molten metallic core, and it functions as a shield against the solar wind, the constant stream of charged particles blasting out from a star. Without a strong magnetic field, a star's radiation and particle wind can gradually strip away a planet's atmosphere over millions of years, which is very likely what happened to Mars, a planet that once had a much thicker atmosphere and possibly even liquid water on its surface until its magnetic field weakened and its atmosphere was eroded into space. The community, having clearly done their homework on this, overwhelmingly voted for a strong magnetic field, roughly 1.5 times the strength of Earth's own, reasoning correctly that a larger, more massive rocky planet would likely retain a hotter, more active molten core for longer, generating a more powerful and longer-lasting magnetic dynamo. Rotation period was next, essentially deciding how long a single day on this planet would last, and the community chose a rotation period of 22 hours, close to Earth's own 24-hour cycle. This decision matters because a reasonably fast rotation prevents extreme temperature swings between day and night, distributes heat more evenly, and avoids the tidal locking problem we discussed earlier with red dwarf systems. A day that is too long allows one side of the planet to overheat while the other freezes, and a day that is far too short creates violent atmospheric wind patterns and extreme Coriolis effects that can generate constant, ferocious storms. Axial tilt came next, and the community chose a tilt of 20 degrees, slightly less than Earth's own 23.5-degree tilt. This produces noticeable seasons without the temperature extremes that a more dramatic tilt would create. A planet with very little axial tilt would have almost no seasonal variation at all, which sounds pleasant but actually reduces certain forms of biodiversity that rely on seasonal cycles for reproduction, migration, and dormancy periods, while a planet with an extreme tilt, similar to Uranus, which is tilted almost completely on its side, would experience brutally long seasons with months or even years of continuous daylight, followed by equally long periods of darkness at higher latitudes. Moons were next, and this category produced some of the most passionate debate in the entire community discussion. The audience ultimately chose for this planet to have a single moon, about 40% the size of our own moon, orbiting at a distance that produces noticeably strong tides. This decision is scientifically loaded with implications, because our own moon is now widely believed by planetary scientists to have played a critical stabilizing role in Earth's axial tilt over geological time, preventing the kind of chaotic wobbling that a moonless planet, or a planet with a very small moon, might experience over millions of years. Tidal forces from a moon also churn coastal ecosystems, which many biologists believe may have played a role in helping early life transition from oceans onto land. A single moon of moderate size, as this community chose, strikes a nice middle ground, providing stabilizing tidal influence without the more extreme tidal heating and volcanic stress that a very large or very close moon can cause. And finally, the community had to decide on ocean coverage, choosing what percentage of this planet's surface would be covered in liquid water. After considering the elevated atmospheric pressure and the slightly warmer orbital position, the audience chose 65% ocean coverage, just slightly more than Earth's own 71%, but distributed across several large interconnected seas rather than a small number of enormous single oceans, which the community reasoned would help regulate regional climate more evenly across the different continents. So there it is. That is the planet you built, piece by piece, choice by choice, across an entire community discussion. We gave it a name, Kepler-9 Terra, in honor of the mission that has discovered so many of the real exoplanets that inspired this whole project. Let me now walk you through what happened when I actually ran this planet through a full climate and habitability simulation, because building the parameters is only step one. The real test comes when you calculate what actually happens to the surface conditions over time. The first thing the simulation calculated was equilibrium surface temperature. Essentially, the baseline temperature the planet would settle at based on the energy it receives from its star, its atmospheric greenhouse effect, and its albedo, meaning how much sunlight it reflects back into space rather than absorbing. Given the elevated carbon dioxide levels, the closer orbital position, and the significant cloud cover generated by that large ocean coverage, the simulation produced an average global surface temperature of approximately 16 degrees Celsius, which is remarkably close to Earth's own average global temperature of about 14 to 15 degrees Celsius. This was honestly one of the most satisfying results of the entire simulation, because it meant the community, through pure collaborative reasoning and debate, had built a planet whose average temperature fell almost perfectly within the range considered ideal for liquid water and complex biological chemistry. Next, the simulation modeled atmospheric stability over a projected span of several 100 million years, factoring in atmospheric escape rates influenced by the strong magnetic field, the star's flare activity, and the planet's gravity. Because of the community's smart choices, a strong magnetic field paired with high planetary mass, the simulation showed remarkably slow atmospheric erosion, projecting that this planet would retain a stable, breathable-style atmosphere for well over 4 billion years, comparable to or even exceeding Earth's own atmospheric longevity. This is a genuinely impressive result, because many of the community-submitted planet designs I tested behind the scenes while preparing this video did not fare nearly as well. Some lost significant atmospheric mass within a few 100 million years due to weak magnetic fields or excessive proximity to more violent stars. Now here is where the story gets more interesting, because no simulation is complete without stress testing, and I wanted to see how Kepler-9 Terra would handle realistic astronomical hazards, the same kinds of hazards that real planets have to survive across billions of years. The first test was stellar flare activity from Hellion Minor. Even though orange dwarf stars are calmer than red dwarfs, they still produce periodic flare events. The simulation modeled a significant flare event roughly once every 11 years, similar to our own sun's activity cycle, and thanks to the strong magnetic field, the simulated atmosphere absorbed the vast majority of the resulting radiation and charged particles, with only a modest increase in upper atmospheric ionization, similar to how Earth experiences beautiful but harmless auroras during solar storms. The second stress test was axial stability over geological time, checking whether the Moon's gravitational influence would keep the 20-degree tilt reasonably fixed, rather than drifting chaotically. The way Mars's tilt is believed to have shifted dramatically over millions of years due to its lack of a substantial moon. The simulation showed that the chosen moon, despite being smaller than our own, was massive enough relative to the planet to keep axial wobble within about 2 degrees over a 100 million year span, which is an excellent result and would allow stable, predictable seasonal cycles to persist long enough for complex ecosystems to establish reliable biological rhythms. The third and final major stress test was what planetary scientists call a runaway greenhouse check, essentially asking whether the combination of orbital distance, atmospheric composition, and cloud cover might push the planet toward the kind of catastrophic overheating that turned Venus into the 460 degrees Celsius hellscape it is today. This was the moment I was most nervous about, because the community had chosen a slightly closer orbital position specifically to compensate for the cooler star, And there is always a risk that a small miscalculation in these choices could tip a planet from pleasantly warm into catastrophically overheated. But the simulation results came back favorably. Because Hellion Minor is genuinely cooler and dimmer than our own sun, the closer orbital position did not push total incoming energy beyond safe limits, and the higher cloud cover actually provided a valuable negative feedback loop, reflecting more sunlight back into space as temperatures rose slightly, preventing the kind of runaway feedback loop that doomed Venus. Putting all of this together, the simulation produced an overall habitability index, a composite score based on temperature stability, atmospheric longevity, radiation shielding, and geological activity levels. And Kepler-9 Terra scored remarkably high, landing in a range that real planetary scientists would classify as highly promising for supporting complex, oxygen-breathing, multicellular life, not just simple microbial organisms, but potentially something approaching the biological complexity we see across Earth's own biosphere. Now, I want to be completely transparent with you about something important, because good science requires intellectual honesty, and that is the fact that this simulation, while built using real astrophysical equations and real planetary science principles, cannot account for absolutely everything. We do not fully understand the exact chemical pathways that led to the origin of life on Earth. We do not know for certain whether the conditions we consider ideal are the only conditions under which life can emerge. And there are almost certainly forms of biology we cannot even imagine that might thrive under conditions our simulation would flag as hostile. This experiment is not proof that Kepler-9 Terra is real, or that life would definitely emerge there. It is a demonstration of how astrobiologists actually approach the question of habitability, using the best physics and chemistry we currently understand to make an informed, rigorous, evidence-based prediction. What makes this whole project even more fascinating to me is how closely some of the community's choices mirror real exoplanets that astronomers have already discovered. The choice of an orange dwarf star closely resembles systems like the one hosting Kepler 442b, a real exoplanet orbiting a K-type star that many astronomers consider one of the more promising habitability candidates ever found. The decision to lean toward a super-Earth mass echoes real discoveries like Kepler 452b, sometimes nicknamed Earth's older cousin because of its similar size and its position within its star's habitable zone. And the emphasis on a strong magnetic field mirrors ongoing scientific debate about planets like Proxima Centauri b, where astronomers remain uncertain whether that world could have retained enough of its atmosphere to support life, precisely because we do not know the strength of its magnetic field. I think what this experiment really demonstrates, beyond just being a fun collaborative project, is just how many interconnected variables have to align correctly for a planet to become genuinely habitable. It is not just about distance from a star, and it is not just about having liquid water. It is a complex, layered puzzle involving stellar type, orbital mechanics, planetary mass, atmospheric chemistry, magnetic field generation, rotational dynamics, axial stability provided by moons, and long-term geological activity, all of which have to line up in a fairly narrow window simultaneously, and for long enough, measured in billions of years, for complex life to actually have time to evolve. This is part of why many scientists who study the rare Earth hypothesis argue that even though the universe likely contains billions of potentially habitable planets, the fraction of those that actually develop complex, intelligent life may be far smaller than optimistic estimates once suggested, simply because so many of these variables need to align correctly at once. At the same time, I want to leave you with a sense of genuine wonder rather than pessimism, because what this whole project shows is that the universe does not need a miracle to produce a world like Kepler-9 Terra. It needs the right combination of very natural, very physical, very explainable conditions that we now know, based on missions like Kepler, TESS, and the James Webb Space Telescope, are not rare in an absolute sense, because we have already confirmed thousands of exoplanets, and a meaningful fraction of them sit within or near their star's habitable zone. The sheer scale of the universe means that even if only a tiny fraction of a percent of planets meet all of these criteria simultaneously, the raw numbers involved, hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe, mean that worlds like the one you just built together are almost certainly out there, right now, somewhere, orbiting some real star we have not yet even detected. Before I close this out, I want to say something directly to everyone who took part in the voting, the discussions, and the debates that shaped this planet. What you built together was not just a fun exercise. It was a genuine demonstration of how collaborative scientific reasoning works, weighing trade-offs, understanding cause and effect across interconnected systems, and making informed decisions based on evidence rather than guesswork. That is exactly the kind of thinking that professional astrobiologists engage in every single day as they search for real habitable worlds among the thousands of exoplanets we have already discovered and the countless more we have yet to find. If this kind of deep dive into planetary science and exoplanet habitability is something you want more of, make sure you are subscribed, because we have several more crowdsourced simulations planned, including one where the audience will design an entire alien ecosystem from scratch based on the atmospheric and gravitational conditions of the planet we just built together. And another where we will simulate what would happen if we tried to move this exact planet into a completely different star system altogether. Thank you for building this world with me. Thank you for the incredible depth of discussion you brought to every single one of these decisions. And I will see you in the next one, where we take this even further. Image prompts.